There's something special about the V12s of World War II. Maybe it's the way they sound, or that they eventually put out well over 2,000 horsepower, powering many of the best fighters on both sides of the war. Or maybe it's because that even 85 years later today, these V12s still fascinate engine and aviation enthusiasts like nothing else can. In this video, we'll go over a brief history of the Aero engine development factors that paved the road to these powerful V12s. And then we'll get technical on why V12s like the Allison V1710, the Daimler-Benz DB600 series and the Rolls-Royce Merlin made such great platforms to push huge horsepower numbers, and what that meant for the aircraft it powered. The need for more powerful engines is something that has gone hand in hand with aviation since even before the first powered flight of 1903. But for obvious reasons, these engines needed to be kept as lightweight as possible, and this complicated the pursuit of more power. During World War I, this pursuit intensified. After all, having more powerful engines available to use on aircraft than the enemy proved to be a good advantage, allowing bombers the possibility of outrunning enemy fighters, and especially in the dogfighting arenas. The fighter with the best performance controlled the fight. This is because more power usually resulted in the ability to outclimb and or outrun the enemy, giving its pilot the choice of when to engage and when to break off. Sure, lighter, nimble fighters could outmaneuver the enemy in the dogfight, but they did not have the option to disengage at will, as the faster enemy could give chase and catch up. This was a dangerous situation for all but the best fighter pilot aces. And since most fighter pilots were not aces, for Aero ministries this shifted the focus away from these lightweight but low power rotary engines which powered these very maneuverable early and mid-war fighters. This was the time of the inline and radial Aero engines. I won't cover radial engines as I've already done a video about its evolution, linked in the description of the video. On the side of the inline engines, the first to leave a lasting impression was the inline 6. In fighters like the Fokker D7, it resulted in a virtually unbeatable combination, leaving the D7 as arguably the best fighter aircraft of World War I. V8s like the Hispano-Suiza also made an appearance towards the end of the First World War. But the flat-plane V8's problems with balance meant that it wasn't a truly scalable cylinder layout. And the difficult to manufacture, at the time, cross-plane V8 crankshaft meant that the V8 was virtually skipped over by manufacturers in favor of the V12. The first V12 engine for aircraft was the 90 horsepower Renault 12A, first run in 1911. Various Aero V12s by different manufacturers followed it and powered some aircraft like the Airco DH9A even before the end of the First World War. By the early interwar years, it was clear that the V12 was where the promise of huge power lied. This was evident by the success of V12-powered racing aircraft, and the Schneider Trophy Air Races was won by V12-powered seaplanes in 1920, 23, 25, 26, 29 and 31, which was 50% of all Schneider trophies, the most popular of which were the Supermarine S6 and S6B, the latter powered by the Rolls-Royce R that made an unbelievable amount of power for 1931 of 2,350 horsepower. The seeds of the great V12s like the DB601 and the Merlin had been planted and were growing. In 1932 the prototype of the DB600 first ran, and in late 1933 the Merlin first ran. And I'm doubtful anyone at that time knew just how important these engines were to be 10 years later. But why was that? Enthusiasts already know the development road of the DB600, the V1710 and the Merlin. But we're going to look much deeper, taking a peek into the minds of its designers. So firstly, why was the V12 chosen as a platform? I mean, why not a V8? Why not a V10 or V16? In 1975, a man named John Gall wrote a book with a long title on general semantics in which he said, "A complex system that works is invariably found to have evolved from a simple system that worked." The quote goes on for 2 more sentences and became known as Gall's Law. And even though John Gall wasn't around in the early 30s when these famous V12s were designed, his idea was most certainly known to great designers back then. And in a few minutes, it will make sense why I say this. To understand the properties of a V-engine of any amount of cylinders, it's best to break it up into individual rows. A V12 consists of 2 rows of inline 6s shaped in a V around a crankshaft. A V10 consists of 2 inline 5s, a V8 2 inline 4s, and so forth. By placing 2 rows of cylinders around a crankshaft, the properties of those 2 inline rows are inherited by the V-engine. For example, an inline engine with bad balance is very likely to maintain that bad balance when using 2 of those rows in a V-engine. There are some exceptions here which I will get to, but this is because in a V-engine the cylinders aren't opposed like on a boxer engine, and the cylinder rows thus can't be used to cancel out each other's imbalance. Inline engines, without using a balance shaft, are mostly unbalanced in one way or another. By the way, balance shafts in aircraft engines are virtually unheard of and is not a good solution. A single cylinder is horribly unbalanced. Inline twins have a rocking couple, inline 3s have a rocking couple, inline 4s have good primary balance but bad secondary balance, and the inline 5 also has a rocking couple. But what about the inline 6? I've already discussed the balance of the inline 6 in a dedicated video, but I'm including it here again for anyone not familiar or who would like a refresher, as knowing the balance of the inline 6 is important to understanding some of the major design decisions of these V12s discussed later in the video. But if you don't want to go over it again, feel free to skip to this timestamp in the video. There are different causes of engine vibration, the biggest being caused by the mass of the reciprocating components like the pistons accelerating, stopping and changing direction, as well as rotating mass like the crankshaft and bottom ends of the conrods. A full cycle of a 4-stroke engine is 720 degrees, and having 6 cylinders means the crankshaft or crankpin offset angle is 120 degrees. 360 degrees divided by 120 degrees is 3, meaning there will be 3 crankpin offset angles, and with 6 cylinders it means that the pistons will move in 3 pairs of 2. Thus, since we have an even number of cylinders and an equal crankpin spacing of 120 degrees, the pistons fully cancel out each other's momentum, resulting in perfect primary balance. Secondary balance has nothing to do with the momentum of the pistons, but instead are all about the non-uniform piston acceleration caused by the conrods tilting side to side. When a piston moves from 0 degrees to 90 degrees of crankshaft rotation, the conrod tilts sideways and thus gets shorter in vertical length compared to its vertical length when it is upright, which is at top dead center and bottom dead center. Because the conrod virtually gets shorter at exactly 90 degrees of crankshaft rotation, the piston is actually pulled more than halfway down the cylinder. Then going from 90 degrees to 180 degrees of crankshaft rotation or towards bottom dead center, the conrod goes straight again and becomes longer again relative to its vertical length when fully tilted. The reverse then applies as the piston moves up again. This results in a longer distance covered by the piston at the top half of the cylinder up and down than the bottom half. Considering that the crankshaft rotates at uniform speed, the additional distance is covered in the same amount of time. That means the pistons moves faster at the top half of the cylinder than the bottom half. This causes tiny vibrations, which gets bigger the higher the mass of the pistons and the higher the engine RPM. Determining the direction in which the secondary imbalance force is enacted is simple. With an engine running, when the conrod is upright, the imbalance force will be in an upwards direction or away from the crankshaft. And when fully tilted midway up or down the cylinder, the secondary imbalance is in a downwards direction or towards the crankshaft. The inline 6, however, with its pistons 120 degrees out of phase, means when two pistons are at top dead center, none of the other four pistons are at bottom dead center. And again, with any two at bottom dead center, no pistons are at top dead center, meaning the secondary imbalance of each pair of pistons are fully cancelled out. Why is any of this important? Smooth running is one factor that significantly contributes to engine reliability and longevity. This is because vibration will eventually break any mechanical fabrication, and the stronger these vibration forces, the quicker this will happen. And when pushing an engine to create massive amounts of power, it becomes even more important that it is a smooth running layout to start off with. Thus, the inline 6 is the least amount of inline cylinders that can achieve smooth firing and perfect balance without a balance shaft, and thus forms the smallest and simplest perfect foundation possible to use multiple of in a single engine. It's the simple system that worked, referred to in Gall's law. These properties of the inline 6 are inherited by the V12, and with the V12 hardly being any longer than the inline 6, the V12 is a perfectly balanced and a much more power-dense package than might be apparent at first. And the V12 is the complex system that works because it's made up of simple systems that worked. The most common V angle is 90 degrees, but there are three factors that designers consider when choosing the bank angle of a V engine. First is size. The larger the bank angle, the more horizontal space an engine needs on an airframe. The second factor is engine balance. With a 90-degree V angle, the crankshaft counterweights can be used to balance out any inherited imbalance from the two inline rows. This is the exception I referred to earlier and doesn't apply to any bank angle other than 90 degrees. Let me explain. Normally, crankshaft counterweights cannot be used to cancel out both the piston's momentum as well as the rotating mass. If it could, there would have been perfectly balanced one-cylinder engines, which there isn't, at least not without a balance shaft. Usually, the main function of the crankshaft counterweights are to allow smooth and balanced crankshaft rotation. Since the conrod's big end has significant mass, it causes an imbalance when it spins. That's not an overall imbalance that causes vibration, because the other conrod big ends will balance it out along the span of the crank, but it's an imbalance in its own plane of rotation, which increases torsion on the crankshaft. With crankshaft counterweights employed to balance out the rotating mass, it can't also be used to cancel out all of the piston's imbalance. That is, unless it's a 90-degree V. This is due to the one crankshaft counterweight cancelling out piston 1's imbalance at top dead center and simultaneously also cancelling out the big end of the conrod of piston 2. Assuming the crankshaft counterweight has the correct weight, it balances the rotating mass as well as the reciprocating mass, which is a unique feature of a 90-degree V engine. It will thus be tempting to use a 90-degree V angle to have the crankshaft counterweights available to remove any of the inherited imbalances from the inline rows. The third and most important factor determining the V engine's bank angle is cylinder firing interval. Inline engines usually have an even firing interval, but this doesn't automatically carry over when using two inline rows in a V. And the angle of the V will determine if an even firing interval is possible. In V engines, the conrods of the opposing pistons will share a crankpin. And we already know a V12 uses the same crankshaft layout as the inline 6 with crankpins rotationally separated by 120 degrees. So if a 90-degree V are to be used for the V12, would it result in a smooth firing interval? To determine this, we take the total revolution of a 4-stroke engine, which is 720 degrees, and divide it by the number of cylinders. For the V12, this is 60. This means that a piston needs to be at top dead center, ready to be fired every 60 degrees of crankshaft rotation. But with a bank angle of 90 degrees, After 60 degrees rotation, an additional 30 degrees of rotation is required to get the piston to top dead center. And then another 30 degrees later, the next piston is ready to be fired. This results in the 90 degree V12 having a firing interval of 90-30, 90-30, which is an uneven firing interval and is undesirable, especially on aircraft engines. So a 90 degree V angle is not ideal to use on a V12. So we can't use the 90 degree V angles property to cancel out any imbalance. But wait, you'll remember from the balance section of the video that the inline 6 on each side of the V12 has perfect balance. So we don't need to use the 90 degree V angle. A V12 of any bank angle will be balanced, but the best choice of bank angle would be the angle that also provides an even firing interval. And we know the bank angle on engines like the Merlin, V1710 and most other V12s is 60 degrees. The total 4-stroke revolution is 720 degrees. Divided by the bank angle of 60 degrees is 12, which is the amount of cylinders on the engine. We also know that these V12s use the same crank pin separation as the inline 6, which is 120 degrees. The crank pin separation of 120 degrees divided by the bank angle of 60 degrees is 2, meaning the engine will fire 2 cylinders every 120 degrees of crankshaft rotation, which is 1 cylinder every 60 degrees. The firing interval thus is a smooth and even 60-60-60 and explains the almost universal usage of the 60 degree V angle on V12s. Next we get to some uniqueness of the World War II V12s. On V engines, opposing conrods usually share a crankpin, with the rod big ends connected to the crankpin side by side. This is relatively affordable and easy to manufacture. However, this was not a common way to connect conrods to a crankshaft around World War II, and back then the most popular conrod setup was something known as fork and blade conrods. Fork and blade conrods are two different shaped conrods used on the left and right cylinder banks, and is exactly aligned unlike normal side-by-side conrods. This is accomplished by the big end of the fork rod being split and the big end of the blade rod fitting inside it. The Merlin, Griffin, V1710, DB600 series and Jumo 211 all had this conrod arrangement. Fork and blade conrods are clearly more complex and more expensive to design and manufacture than side-by-side conrods. The fork and blade pair is likely also heavier and in the case of some engines requires enhanced oil flow. So why was fork and blade conrods used in these V12s? The first reason that is frequently given is to reduce engine length. But fork and blade conrods would not substantially shorten the length of the V12, probably less than an inch, if at all. Side-by-side conrods might at first seem to take up more space, but keep in mind that the fork rod is generally wider than a normal conrod, as the blade rod needs to run inside it. But these V12s are gear-reduced engines, with the gear reduction units placed on the front of the engine, making these engines quite long. And so one could argue that reducing the length of these engines even by an inch makes a useful difference. Another benefit of a shorter engine, albeit less tangible, is the crankshaft will be shorter. V12s have very long crankshafts, and shortening it in theory makes it stronger. Besides that, fork and blade conrods creates less uneven load on the crankshaft, specifically less twisting force on the crank pins than a normal side-by-side conrod setup. With fork and blade conrods, the power pulses from the piston via the conrod are thus applied exactly in the center of the crank pin. This is significant because on a V12 like the Merlin, every piston produces around 120 horsepower. It also results in the load on the bearing being more spread out, as the bearing would have more surface area on the crank pin than it would have in the case of side-by-side conrods. The crankshafts can thus in theory be made lighter, since fork and blade conrods are more gentle on the crankshaft. Then thirdly, there's a benefit to using fork and blade conrods that seems to me are often misunderstood. And that's the opposing cylinders and pistons being exactly aligned longitudinally. When using normal side-by-side conrods, the pistons and cylinders can't be truly opposed and will be slightly offset. I often hear and read that the benefit of exactly opposed banks on a V12 is that it gets rid of the rocking couple. That would be true of, for example, a Harley-Davidson V-twin that makes use of fork and blade conrods to get rid of the rocking couple. But on the V12, this makes no difference. You'll remember from the balance section of the video that each bank of inline sixes are perfectly balanced. So it doesn't matter how far offset the banks are, there are no unresolved forces on the V12 that can create a rocking couple, even with offset cylinders. However, there are some other benefits to not having the cylinder banks offset, like easier block manufacturing and even makes the block slightly lighter, as offset cylinder blocks will have dead metal on one side of each block that does not offer any benefit to the engine. Naturally, not having offset cylinder blocks also makes the engine slightly shorter. Besides all of these valid engineering reasons for using fork and blade conrods, there is another likely reason that they were used, one that might be more difficult to accept. That is, fork and blade conrods were used because, at the time, it's the way it's always been done. It was a well understood and well trusted setup. There is little reason the DB601, the Merlin or any of these V12s would have been any less powerful or reliable using normal side-by-side conrods. All V12s mentioned so far have the same valve train arrangement. Single overhead camshaft per cylinder bank with 2 intake and 2 exhaust valves per cylinder. An overhead cam valve train, apart from being bigger than a pushrod or overhead valve system, has fewer moving parts than a pushrod system. Additionally, using more than 2 valves per cylinder on a pushrod valve train becomes quite complex and further increases the number of moving parts. Overhead cams have been used on most V12s pretty much since the first Aero V12s were made, with the total number of valves per cylinder soon being increased from 2 to 4 to increase volumetric efficiency, which basically refers to the efficiency with which air are moved into and out of the combustion chamber. Between the Merlin, the DB600 series and the V1710, the Merlin is the smallest with a displacement of 27 liters. So these engines needed to pull in massive amounts of air at full power. It also moved massive amounts of spent air out of the exhausts every second. These exhaust gases exited well in excess of 1000 miles per hour, and it was realized that this could provide useful thrust by angling the exhausts backwards as well as shaping the exhaust stubs for optimal thrust. During tests on the Spitfire, it was determined that about 70 pounds force was exerted by the exhausts at full power, with the exhaust thrust alone increasing the max level speed of the Spitfire by 10 miles per hour. A subject that has been debated for many decades is which of the World War II V12s were the best. It's sort of silly though, because as long as the V12 was of a reasonably good design, there was one thing that influenced total power output much more than anything else. I'm of course referring to forced induction, of which there are 2 types, supercharging and turbocharging. The 2 terms are sometimes used interchangeably, but there is a distinct difference which we'll get to. Even the best V12 design with suboptimal forced induction were pushing meager horsepower numbers. Additionally, the air war was often fought at over 30,000 feet, where air density is about a third of air density at sea level. Naturally aspirated engines loses roughly 3% of its power for every 1,000 feet it climbs due to decreasing air density. And by the time 30,000 feet is reached, 90% of the engine's power is lost. Thus, most naturally aspirated engined aircraft can barely reach 15,000 feet, much less carry a load of bombs that high or dogfight up there. But with forced induction, the less dense air at these altitudes are compressed, allowing the engines to make full power up to about 15,000 feet, as if at sea level. And by adding a second stage of forced induction, high power was maintained up to 30,000 feet. The main difference between a turbo and a supercharger is driven mechanically by the engine, and a turbo is driven by exhaust gases. Since superchargers are driven by the engine, most of them provide a linear increase in boost as engine RPM increases. But it takes some of the engine's power to drive the supercharger, which is a parasitic load on the engine. In the case of the Merlin, its two-stage supercharger saps in the region of 400 horsepower from the engine. A turbo, on the other hand, has no parasitic load on the engine as it uses spent exhaust gases to drive it. However, it requires the engine to run at relatively high RPM to start moving air to provide boost. Thus, at low RPM, lag is experienced, often referred to as turbo lag. However, as airplane engines are mostly operated at relatively high and constant RPM, turbo lag is a total non-issue in aviation. So why then did most of these V12s use superchargers instead of turbos, which clearly seem like the better option? Rolls-Royce did a lot of experimenting with turbochargers as far back as the mid-20s. However, suitable turbos had a few problems. Firstly, they were massive. When the Allison V1710 was designed, the idea was to use a supercharger in conjunction with a turbo. Allison's engineers created only the second stage of a two-stage forced induction system, a supercharger, and then a General Electric turbo would be supplied as the first stage of forced induction. With the advantages of a turbo, on paper this seemed like a great idea, but it wasn't really apparent how large this turbo would end up being. And despite trying, there was no space on American fighters like the P-39 and P-40 to house a turbo of this size. On the P-40 Warhawk, they did attempt it on the J variant, but when they realized that there was simply nowhere to put the massive turbo, the project was cancelled without anything being built. The P-39 Aero Cobra was designed with the turbo-supercharged V1710 in mind right from the start. But as we know, it went into production without the turbocharger due to the complications of housing a giant turbo. As a result, these aircraft were doomed to have single-stage superchargers without the turbo for the duration of the war. This resulted in poor high-altitude performance, relegating these fighters to either secondary use or primary use in other theaters of the war where high-altitude operation wasn't as important, like the Pacific theater. The same problem existed on the Spitfire and Hurricane, as there simply was nowhere to put a massive turbo, which is one of the reasons why Rolls-Royce wisely very early on abandoned the idea of a turbo-supercharged Merlin. Additionally, it was quickly pointed out that a turbo uses the energy of spent exhaust gases to run it, and on the Merlin-powered Spitfire and Hurricane, this energy was already being utilized to create exhaust thrust, as mentioned earlier. When adding a turbo, that energy would be used to spin the turbo instead of creating exhaust thrust. This made the case for turbocharging even less attractive for this application. When it comes to superchargers, there are three types, and the one that was used on these V12s was the centrifugal supercharger. That's the supercharger that looks like a turbo and functions much like a turbo, other than being mechanically driven by the engine instead of by exhaust gases. The centrifugal supercharger had some of the same problems as a turbo, being inertia to spin up the air, resulting in lag. But as said before, on aircraft this really isn't a problem, with the engines operated at relatively constant high RPM in most stages of flight. Centrifugal superchargers are more thermally efficient than the Roots and twin screw type superchargers. Heat is energy lost, and it's energy that isn't converted into mechanical power. Not only that, but centrifugal superchargers have less heat transfer between the supercharger and the engine. It seems like the obvious choice for forced induction on the V12 engines. The V12 in isolated cases did remain in military service long after World War II. An example being the Rolls-Royce Griffin-powered Aero Shackleton, being in use by the South African Air Force until 1984 and by the RAF until 1991. But of course, the writing was on the wall for high-power piston engines in the military by the late 1940s already, with the advent of the turbojet engine, which were much more reliable and powerful than even the most powerful V12s. But what about modern aviation V12s? There's a few actually, with the most popular probably being the red A03, hailing from Germany. The V12 from Red is a diesel V12 that made its first flights in the 2010s on a Yak 152 and got some spotlight in the early 2020s, powering at least one air tractor crop duster as well as a de Havilland Beaver, among a few others. The A03 is a compression ignition or diesel engine running primarily on Jet A fuel with the capability to run on sustainable aviation fuel. It gives 20 to 40% better fuel consumption than the Radial engines it replaces and up to 50% better fuel consumption than the other alternative, which is turboprop engines, and thus lowers operating cost significantly. It's a turbocharged 6.1 litre 80-degree V12 gear-driven double overhead cam, so no timing belt or chain. It weighs 363 kilograms or 800 pounds and puts out 500 horsepower for takeoff at 4000 RPM, depending on which version of the engine. Specific fuel consumption is 0.35 pounds per horsepower hour at 400 horsepower. Another modern V12 example is from Norwegian company Aerosport Engineering AS and is a supercharged 60-degree V 5.4 litre chain-driven single overhead cam that outputs 683 horsepower at 5200 RPM. The engine is based on the BMW M73-B54 as originally found in the BMW 750, produced from 1993 till 2002. If you're worried about the engine being auto-converted instead of being designed as an Aero engine from the start, take a look at their website. It is the most detailed technical website I've ever seen of any engine. It contains photos and details on just about every component you can think of, with pages long of details about its engineering, why they chose specifically this engine, and modifications made to it. I hope you found my endless blabbing about V12 Aero engines informative. If you did, you'll also like these videos. Thanks for watching and see you in the next one.